I mentioned quickly going out the door the other day that we're going to switch gears, no pun intended. Yeah, it was intended. And start talking about the motion that is rotational. And of course, I think with an illustration like this in front of you, I think it helps a lot to understand that. But that, in some respects, this connection between linear and rotational velocity and acceleration is the backbone of the culture we live in, because that's what's happening inside your car. Basically, there's an explosion that causes linear motion. Explode, the piston moves away. That's linear motion. But somehow we figure out a way to get that to turn into rotational motion, connect it to the wheels, and whoosh, down the road we go. And the same thing is true here. Like I'm rotating, I'm pushing on the front of that crank up there, and then the chain has got linear motion to it, but then so are the wheels. And so, you know, the fact that I'm cranking rotationally, but yet I'm linearly moving down the road, I mean, that's just really cool. And so the fact that, not just the fact that, you know, things can rotate, and we have to have some way of talking about, you know, what the quality of that rotation is. Do they rotate fast? Do they rotate slow? Are they increasing? Are they decreasing in that rotational speed? That's cool in and of itself, and it makes sense we might need to describe that. But on a larger scale, it's kind of like, well, yeah, who cares though? What are we doing with this? So, you know, when you look at it in the form of a bike or a car, a bike is just cool because it's kind of transparent. That's kind of neat. So what I want to start off with, we'll get back to this in just a second because I've got gears on here and distances in the chain and so forth. And, you know, we're going to learn this in context of a bike, sort of a way more interesting problem than I think you're going to get in your assignment. But what I want to stare at for a second here is in your dynamics formulas. We are on chapter 16, the final chapter. And I want you to stare at these formulas right here because I want to build these with you, for you. I want you to have a sense of what they come from, where they are. So let's just kind of stare at them for just a second. Omega. Let's see. Maybe I'll switch to a blank piece of paper, but that W is omega, which is the change of angle over time. So if I'm changing my angle as I'm doing in this chair right now, if I'm changing my angle as a function of time, does it make sense? That's your rotational speed. So rotational speed or angular velocity is kind of the word you'll hear in the book. And so omega is the Greek letter that's ascribed to that. But then notice also, although I might be traveling at a constant angular velocity as I'm rotating, like I am right now, does it make sense I can also speed up? I can say, oh, that's not fast enough, I want to go faster. So there's also alpha there in that note sheet, which is, you know, kind of the symbol that's used for angular acceleration. So if you change your angular speed over time, then that means you're accelerating. Now that's not brand new. We used alpha for that, didn't we, in another class? Angular, I think we did. And then notice the analogous formulas. Like these two formulas here should look similar to you. Like didn't we have a velocity one that said velocity equals acceleration times time plus initial velocity? Isn't that exactly the same formula right there? Except for here, velocity is, well, angular velocity. And then notice why they used alpha now, because A for acceleration, well, alpha is the Greek letter for A. So that's what that's doing there. I actually don't know why omega, the W, if you will, omega is used. It seems like it'd be some Greek letter that started with B. But notice the same thing is happening down here. Wasn't this position equal to 1/2 times acceleration t squared time plus the initial velocity times time plus the initial position? Well, all we're talking about now is position now is relative to an angle. Quick side note, I'm laying, I don't know if I told you guys this, I kayaked the Illinois River this weekend, and I went to bed, and we were talking about the stars as we went to bed and how the tip of the Big Dipper looks something like that, if I remember right. This front right here actually points to the North Star. Is that something you know? So, you know, we're just laying there going, oh, cool, that's the North Star. It's really big. And, you know, I'm used to seeing, for instance, the moon go across the sky and the sun go across the sky. And every time I look for the Big Dipper, I have no idea where it is. Like I'm not into astronomy. So it's kind of like, you know, I'm looking up and over my head. And of course, different times of night, you know, and different times of year, it is in a different location. So that kind of makes sense. But what was weird is I woke up later in the nighttime. And this is like a revelation to me that I just never even understood. The Big Dipper was in this position, basically, something like that. And basically, those two stars still pointed toward the North Star. So I'm used to just thinking of stuff as like moving across the sky. And again, we think of it, you know, human-centered, like somehow it's moving for us to watch when actually we're spinning and it's just sitting there, right? But it actually rotated. I mean, that's the thing that kind of just freaked me out. Like it was facing something like that instead of the way it was facing before. And so I realized, wow, the North Star is called the North Star because it actually stays in the north. Like it doesn't move across the sky. It's always there because we're actually, it must be above the North Pole and spinning. And so anyway, you know, again, I'm looking at that rotation. It was kind of weird as I was laying there. I was thinking, wait a second, it takes 24 hours for the Earth to rotate one time around. And so I looked at, you know, my memory was it was sitting over here and now it's over here. And I was kind of looking in the sky thinking, yeah, it's like, I don't know, 70 degrees or something like that. And I was thinking like, wow, I think I could figure out what time it is right now because I knew what time I went to bed. And I was like, sure enough, I looked at my watch and, you know, so this angle stuff is kind of fun. I mean, it shows up in lots of different places, but you know, what we're talking about here with respect to theta is just the position something is in. Like at night, you know, when I looked up at it, the position of one, you know, of those two stars that pointed toward the North Star was here, and then later it was over here. That was 70 degrees apart. So, you know, where is something rotationally is what theta is really all about. So what I want to get at now, though, is just these equations. So you might be staring at those in your note sheet, but I just want to, it's like, what are these? And at a glance, what I want you to notice, the thing that's really cool is notice this is how you convert worlds, because V is linear, whereas omega is angular. So this is actually the connection between angular and linear speed. And as I said, in the case of a bike, if my wheel is rotating angularly, the fact that I can actually turn that into my speed going down the street is rather cool, isn't it? And notice the same is true for the next equation. Linear acceleration and angular acceleration are also related. And notice all I have to do is multiply by the radius to get that answer. And so this is kind of cool. These things are related. It kind of makes sense, right? You spin the pedals faster, your bike's going to go faster. But, you know, this is actually the math as to how that's actually connected. Without putting you on the spot, is this something you studied in physics? Like I took physics when I was your age, so I don't even know. What's that?
I didn't take physics.
Okay. Did you?
Not the connection between the two, but yeah.
So let's just play with that a little bit. Just kind of give you a chance to soak on this a bit and understand this. So really theta is equal to the position. It's the position, except kind of like in angle land or something like that. Maybe I'll say it a little more profoundly. I'm just making this up, but in a rotational sense, it's like where you are rotationally. That's what theta represents, so angular position. And we'll notice this is often and importantly measured in radians. And so, again, that's fine. Like I'm facing north, sitting in my chair right now. But of course, you might be interested in that moving, rotating, just like the sun. You know, the Earth rotates around the sun. It's actually flying around the sun. It doesn't stay at the same angular location as it cruises around the sun. So I might be interested in, well, in calculus, how's that actually changing? How does angle change? And as I said a second ago, that's what we call omega, which is angular velocity. Angular speed, rotational speed. But you'll see the term angular velocity. Does it make sense if the top is theta, which is radians, and the bottom is time, which is in seconds, that this would be measured in radians per second? Or degrees per second. And then finally, as I pointed out a minute ago, even omega, my rotational speed could change, right? Couldn't I accelerate? Couldn't I speed up how I'm rotating? I mentioned yesterday as we're going out the door, just kind of how skaters, as they're spinning, will pull their arms in, will actually increase their rotational speed. So I might actually even change omega with respect to time. And so if I change my speed, isn't that an acceleration? And again, that's the Greek letter. So that's angular acceleration. Perhaps you can figure out what the units of that would have to be. Since omega is radians per second, and now we're saying per second again, it's radians per second per second. Again, it's way better to write this as radians per second per second. How many radians per second am I increasing per second? As soon as you write it as radians per second squared, all of a sudden, although that's nice and clean, nobody really knows what that means anymore. You understand that logic? Again, we're trying to make sense of things in this class. I mean, you'll see it written that way just out of laziness, but. Okay, so let's play around a little bit with kind of how this all works. We just really gave names to the fact that I have a position, a speed, and a change of speed in this world, and that kind of makes sense why somebody would care about that. But are you aware of this formula? If you have a circle of radius r, and you got some angle there, we'll say radius theta, and this length up here, this arc length, often called S for no good reason. There's a relationship between those. And actually, it turns out that all you have to do is take theta and multiply it by r, and that will actually give you that arc length. For some reason, that looks backwards, so I'm going to turn it around, r times theta. Now, I'm just telling you that. Would you like to know why that's true really quickly? Because it just looks like, you know, a formula. Well, it really has to do with proportions. Like you can build this for yourself. Would you agree that the circumference of that circle is 2 times pi times radius? So the entire arc length is 2 times pi times radius. And isn't the entire angle 2 pi radians? So the entire arc length and angle, we'll see there's a proportion here. Let's see, I should say this differently. I shouldn't call that theta, I should call it like, I'll just say angle. So would you agree that you could say, hey, S is a part of the arc length, whatever proportion S is of the entire arc length, wouldn't that match what theta is of the entire angle? You see the proportion there? S is part of the arc length, 2 pi r is the entire arc length. Theta is part of the angle, 2 pi or 360 degrees is the entire angle. Are you feeling that proportion? Okay, well, cool. Let's just multiply both sides by the fractions and get rid of them. So if I multiplied 2 pi over, it'd be 2 pi s. If I multiplied 2 pi r over, it'd be 2 pi r times theta. Hey, look, those two 2 pi's cancel out. Bam, r times theta's got to be s. So that's a cool shortcut. However, did you notice I used the angle in radians, not degrees? And if I had chosen this 2 pi right here to be 360, does it make sense that wouldn't have canceled out so nicely? So because I chose to put the angle in radians, that means, well, theta is in radians. Like this formula doesn't work if theta is 52 degrees. It's got to be radians or this shortcut doesn't work. So that's just kind of cool.
Just convert.
Exactly. Yeah. So if you had 52 degrees, you could convert it to radians and then you'd be on your way. So that's kind of a cool formula. So let's play with it for a little bit using calculus. So if I said r times theta equals s, would you agree that from last term, that's a static fact? In other words, theta isn't changing, the radius isn't changing, the arc length isn't changing, but could it change? Again, think of this in the solar system somehow. Does it make sense as I was watching a satellite fly over my head out there? Does it make sense the distance that's traveling is actually curved? And so the arc length is getting bigger. And of course, automatically, isn't the angle getting bigger too? So can you let this change? Because I like to explain when I teach calculus, calculus is the mathematics of motion. If those things don't change right there, that's great. And that has application. But when I look out the window, I see some things not changing. There's a building not changing, but then I see clouds moving, I see cars moving, I see people walking, I see branches moving in the wind. Like anything that's changing, you can't do that unless you have calculus. Calculus is the mathematics of change. So if I want this to change, that's what calculus is for. Let's take the derivative of that statement. Now we're going to do this relative to time. Find the derivative with respect to time. Again, this should probably teach you some things about calculus. We teach calculus really not very conceptually sometimes. So in other words, I'm going to find things like ds dt, not ds dr, because I want it changing relative to time. Does that make sense? That's how speed works. I want to know what it is per second, not per, I don't want to know how s changes per r. I don't want ds dr, dr d theta. I want ds dt, dr dt, d theta dt. So based on, well, let's just keep this simple. Let's have r be constant. Now, the reason I'm saying that is because if we're talking about the Earth moving around the sun, does it make sense our radius does stay constant? Like we're actually not getting further and further away. Now, that's actually, I think, slightly not true, but it's roughly true. Or for instance, if I'm talking about a bike tire, is the radius of my tire changing as I go down the road? No. Now, as I said, could it? Yes, and this would be more complicated. If I took the derivative of the left side and I have r times theta and they both change, does it make sense that's a product rule problem? Maybe I'll even write it that way. So the derivative would be, let's let r change, which would be dr dt, but then that would be times theta not changing, plus then the r doesn't change, but then d theta dt does. Does that ring a bell as the product rule from calculus a long time ago? So it's the derivative of one times the other left alone, plus the derivative of the other times the first one left alone. So I'm really just taking the derivative of both sides. In other words, saying how they're changing. But if you said that the r is not changing, does it make sense that dr dt is actually 0? So in my case, I wouldn't even have written that first part of that because we said r is a constant. So I wouldn't have written it, but it's just kind of cool to think about. So here's this equation. Awesome. But didn't we just make up names for this? Like d theta dt, didn't we just get done saying that we were going to call that omega? What about ds dt? What's ds dt? Good job. S is a length. It's a distance. Now it's curved distance, but it's a linear length. You understand that? So that's actually just velocity. So, you know, what does that mean? I mean, let's just kind of take a second. And so here's the Earth flying around the circular, roughly circular path around our star, the sun. This is saying, if you know the radius, then there's a connection between the angular speed. And again, angular speed would be me watching it. I'm looking at it up in the sky and I'm having to turn my eyeballs to watch it go, right? So I'm having an angular speed to watch it. But doesn't this also have a linear speed? If you're standing on the Earth with kind of the wind blowing through your hair, isn't like, whoa, I'm going fast. So isn't there a linear speed and aren't they related? It makes sense they'd be related. Well, calculus gives us the relationship. So this is one of the formulas that was on the sheet that I pointed out a second ago. And do you see that as a conversion, the ability to convert between linear speed and angular speed? And do you see the power of it kind of in that context? The bike tire is rotating at a certain number of radians per second. And based on its radius, the radius of the tire, then I'm gonna, you know, linearly roll down the street, right? Which is why I want the wheel rolling in the first place, so I can end up down the street. So it's the rotational motion that I'm causing is resulting in linear motion. So quite a cool invention, right? That's kind of the idea behind what a bike is doing. Well, let's do that again. What if I take that same exact equation and I'll go a little faster this time and say, well, let's get that moving. Like, does that thing change? Like, do you change your linear velocity and your angular velocity? Yeah, you might do that. Well, let's take the derivative again. Except this time I won't bother with, I'll treat r as a constant, which means the constant comes along for the ride, and omega, if omega changes, then this would be its derivative, the change of, we didn't do anything there, I just said the change of omega over time. The other side would be the change of the velocity over time. But again, don't we have other names for those? Didn't we say the change of angular velocity over time, we call that alpha, because that's an acceleration. And the change of linear velocity over time, isn't that also acceleration? Now, the one important thing I'd like to point out, though, that's actually what we would call tangential acceleration. You understand that? Think about the planet that's moving along. The planet, us, is kind of flying around the sun, and you say, hey, I'd like to change its speed. Remember how we actually described that as tangential acceleration early in this class? That's literally a speed change. But we also said there was this thing called normal acceleration, which was a direction change. Is that ringing a bell? And with respect to that direction change, did we not say, color, did we not say, if I remember right, that AN was equal to V squared over R? Maybe I used rho for radius or something in there instead of R, but isn't that what normal acceleration was? We had a formula for that earlier. We understood that at one time. I've kind of forgotten where did that come from. I don't know about you, but I can't remember where that came from. So, okay, cool. So that formula is great. I could use that. But notice a second ago, we just figured out that V was equal to R times omega. Back up here, right? So what would happen if I replaced that R times omega? Would that be worth anything to do that? Well, notice you have R squared, which cancels with R, which leaves 1R. And then you have omega being squared, which kind of doesn't cancel. So there's kind of another form that you could use. So if I wanted to know the normal acceleration, the direction change, I could take the speed, the angular speed squared and multiply by the radius. So I've got a couple options here. So really those four formulas are formulas that we can build and understand, and it allows us to kind of, understand how speeding up my rotation on the wheels of the bike or on the crank of the bike, the only thing I can control, might result, how's it going to result in me going down the road faster? So let's try to soak that in a little bit. So let's take a look back at the geometry of this particular bike. So we'll go on and do a practical example and try to make this all go into your head a little bit. But notice there's a couple of things, and this is me just taking pictures off the internet and me holding a tape measure to my bike to kind of play around with it a little bit. But let me just point out a couple of things they're going to use in just a second. This thing right here is called the chain ring on a bike. And in my particular bike, that has just got one cog on it. So notice it says right here, that's a 32 tooth chain. So there's literally 32 teeth on it. Now look down here. Do you see how I took a tape measure and put it up to the chain? And it's roughly from center to center about 1/2 inch per tooth. So does it make sense if that's a 32 tooth chain, each tooth is 1/2 inch apart? That's like a 16-inch circumference chain, if you will. So that's kind of cool. And of course, the reason the chain has, cogs or points on it is so that when you pedal, it doesn't slip. So you can have a belt in a car, and if it's not tight, it'll slip. So this isn't going to slip, and you're obviously putting a lot of torque on it. So that's kind of cool that you can kind of make that conversion. So the only and this is specs that I just stole off the internet. So it said 32 teeth, and that's great, but it just doesn't, I need circumference sometimes for some of my calculations. So based on that measurement, that's kind of cool. I can figure that out. Notice the rear cogs, plural, as you may be familiar with on a bike. Back there, you can shift, and some bikes you can shift front and back. But this particular mountain bike, you can only shift back, which is nice because it's one less thing to break when you crash. But notice it says cogs, and this particular one is an 11 speed, and it has at the smallest 10 teeth per cog. Notice it doesn't say teeth here like the previous one did, but those are teeth. Everywhere from 10 all the way up to 42. And it doesn't tell us what's in between. 42 is your climbing gear, so that's a really important one. I think the bike I have now is like a 52, which makes it much easier to climb up something really steep. So there's 11 different cogs there between 10 and 42, but in a sense, the only ones I care about are, well, the only ones I care about is the 42. The 10 is just like for going fast, but that doesn't really matter that much on a mountain bike anyway. It matters like how can you climb. So anyway, that's just kind of interesting. And then the last thing to notice on this that you need to know is the fact that this particular rim right here, the tire is a 27.5, which is a diameter statement. So it's roughly a 2-foot diameter, 24 inches would be 2 feet diameter. That's the size of the diameter of that particular wheel. And so you got the interaction of all this stuff. And maybe you've never played around with the logic as to how this all works before and why it, because this is the same thing that's in your car as a transmission. It's just that on a bike, it's actually transparent. You can see it, which is kind of fun. And I won't go into this, but I took a measurement, the crankset distance from here to here is 7 inches. You should have a sense from this class and from the previous class that that 7 inches is really important for the torque aspect. Like if I have a certain amount of muscle on my leg, which can create force, then it's force times that 7-inch distance. So it's like, you might think, well, why don't you make it 9? Yeah, that's going to give me more force. Problem is it starts hitting rocks on the ground. I've had some really good crashes thanks to that problem. Even at 7 inches, if you lean over and you have that side down, it'll hit rocks, and I went thanks to that. So there's kind of a balance there. Went long, but not too long. We don't need to know that for the problems we're working on, but it's just kind of interesting to think about because your ability to create torque on that chain is based, you're stuck with whatever muscles you got, but you're not stuck with that 7. You could buy something different. Okay. Let us then proceed hence to this first question. So you have this in front of you. So let's just really go slow here and slow me down if I get going too fast. The biker pedals the crankset, so the linear velocity of the chain is 14, and this doesn't say 14 inches per second. It says 14 t inches per second. So if the chain was moving 14 inches per second, that would be cruise control. Does that make sense? It's always 14 inches a second, and that's a common thing to do if you're on flat ground. But notice I said 14 t, which means that 1 second, the chain is moving 14 inches a second, but 2 seconds later, it's moving 28. 3 seconds later, it's moving 42. So this person is accelerating. They're pedaling faster and faster and faster. Sounds unrealistically faster, if it makes sense. Like you're not just going to keep going with that. 10 seconds later, it's 140 inches a second. That doesn't seem, at some point, it's like, come on, man, you can't do that. So in a sense, that's a playful example. And the chain is on the low gear in the back, which is actually the big one, the 42 tooth rear cog. So the front one we already know because we're stuck with it. It was 32, the back is 42, that's the one it's on, and you're pedaling with a certain 14 t inches per second. So let's see, what do I call that 14? Notice it's units, it's very important. I want you to get this on your own. What do I call that? Units. Based on the fact that it's inches per second, what is that telling me about how this person is pedaling?
That's how fast they're moving in your direction.
That's linear velocity. And I told you up here V, but it's It's linear velocity, not angular velocity, because I said the chain was moving like that. Does that make sense? So that's your linear velocity of the chain, not the wheel, not the bike. That's how fast the chain is moving as a function of time. Does it make sense that I could take the derivative of that? The change of velocity over time is tangential acceleration. The derivative of 14t is just 14. And so that makes sense. As I just said a second ago, at 1 second, you're going 14. At 2, you're going 28. At 3, you're going 42. And so aren't you increasing 14 inches per second every second? So the fact that you take the derivative of 14t and get 14 actually makes sense. I can see the acceleration over there. And if you think about those previous formulas we have, didn't they say velocity equals acceleration times time plus initial velocity? So isn't 14 the acceleration? I mean, there's a lot of ways to kind of look at that. So basically, I was given some information about the linear motion of the chain, but nothing about angular. And so then we're told the chain is like sitting on certain cogs and so forth. And so, okay, great. So he starts from rest, that makes sense. And then I'm asking you to convert to, well, the angular world. What's the angular displacement? And again, that's a crazy statement. Angular displacement just means how much does the angle change? Angular velocity and angular acceleration of the rear wheel, which is fixed to the cog. Do you understand that? Do you understand that on a bike? If the cog turns, the wheel's turning exactly the same. They're welded together, so to speak. So the angular acceleration of one is the same as the angular acceleration of the other, but based on the radius, their linear speed is not the same at all. So in a sense, I'm saying you got linear information. Can you convert it to angular? And of course, in this case, that might be interesting to know. Why did I say at 8 seconds at the end of all of that? Why didn't I just leave it at that? Why did I say at 8 seconds? Well, the problem is that as time goes by, is the position of the wheel staying the same? It's like moving, right? So I can't just say where's the wheel. It's like you have to know when. So at 8 seconds, where's the wheel right now? I mean, think of it as like the valve stem that you put the air in. Where's that at 8 seconds? And how fast are you going angularly at 8 seconds? And what's the acceleration at 8 seconds? So I had to pick a time. There has to be a snapshot in time to kind of answer all those questions. Well, let's see if we can use all those formulas to kind of put all that together. So let's see. Let's just figure some random stuff out here. So I said a second ago that that was a 42 tooth cog, and we said that was based on the measurement, that was a ½ inch per tooth. So does it make sense? That makes it a 21-inch circumference. That cog back there at least is behaving as a 21-inch circumference, and you can appreciate because it has cogs on it. That'd be hard to measure because where do you measure to? It's not a circle, it has points. Do you measure from outside point to outside point, or from the saddle on the inside of the chain to the inside? But notice, because I know how long the chain is, that gives me a circumference. And then of course, circumference is equal to 2 times pi times radius. So if I take 21 and I divide by 2 pi, I get the radius of that cog is 3.342.
I kind of missed that. You have 42 and then you multiply by 1/2.
Because I have 42 teeth around the outside of that thing. And what I saw on the other sheet was the measurement from one tooth to the other was a ½ inch. So that means I have 42 ½ inches around that thing. 42 times a half would be 21. Thanks for asking that. Good question. So does it make sense? I was able to figure out and I've got a lot of radiuses here. Like I got radiuses of wheels, all kinds of radiuses. I'm going to call that RC for radius of cog, I guess. Now, again, didn't our formulas that we had a minute ago have lots of radiuses in them? Do you see why I took the time to calculate that? Seems like I might need it for something. Well, let's just consider some of the formulas we had then. Didn't we have one? Well, first of all, I guess maybe I should, because I don't know my velocity yet. Does it make sense? I don't know my velocity until I kind of get to at t equals 8 seconds. Velocity would be 14 times 8, which is 112. And because this was inches, because that's a linear velocity, it's inches, not radians. Inches per second. So at that second anyway, 8 seconds later, that's how fast the chain is going. And didn't I have a formula a second ago that allowed me to convert from linear speed to angular speed based on radius? Again, slow me down, interrupt. So let's go try to find omega, the angular speed. Well, didn't we say that velocity was equal to radius times angular speed? So since I just found out that the velocity is 112, and I figured out a second ago that the radius of that cog, let's see, radius of the cog. The radius of the cog was 3.342. So because I chose the radius of the cog, how come I didn't choose the radius of the wheel? We don't have a number of radiuses to choose from.
Or angular speed.
The reason is that the chain is actually hooked to that cog. You see what I'm saying? It's not hooked to the wheel. So this is actually the angular speed of the cog right here. If I divide those, I get 33.513. And automatically, if you took velocity, which is inches per second, and then you divide it by 3.342 inches, and I want you to pay attention to this. I'm gonna go ahead and write these units in here. Inches per second, this is inches. If I took inches per second and divided by inches, does it make sense the inches would cancel and I'd have nothings per second? That'd be my units, nothings per second. Well, that means we're stuck with radians here. Now, stop and think about that number for a minute. Like, is the cog moving slowly or fast? What does 33 radians a second look like? Do you have any gauge for that? Again, we're just slowing down, like make some sense of this. Well, what's one lap? If something spins one lap, how many radians is that? Pi, yeah, which is 6.2, right? 6.28. So that's 6 radians per second would be one lap. Oh, this is like 5 times that, right? Roughly. This is spinning 5 times in 1 second. So that's pretty fast. Like I'm probably not gonna be able to see it really, right? I'm just gonna see kind of a blur. It's a lot of motion for 1 second. 1,002 went around 5 times. Ooh, that's pretty fast. Now, do you remember in the original question though, I asked for this with the rear wheel, not the rear cog. But as I said a second ago, those are hooked to each other. So that actually is the same. The cog is hooked to the wheel. However angularly one turns, the other turns the same. again, just to kind of make sure you see this. So here's my hand, and we'll say that's like out on the edge of the wheel. And then here's the front of my shirt. So if I start spinning, aren't those angularly moving identically? Yeah, they're moving the same. They're hooked together angularly. Now, are they hooked together linearly? The answer is no. If something small like this rolls one time around, it's not going to roll across the table very far. But if something this big rolls one revolution around, it's going to roll way further down the table. So do you see how the linear conversion is not the same? The angular, they are the same. But linearly, they're not. That's interesting.
We plug in our radius of the tire.
That's right. So see, we could get the radius of the tire involved here. And I didn't ask for this, but let's just do this really quick. If I took the angular velocity of the wheel, we said that a second ago, if you take that and multiply by the radius, that'll give you the velocity. That was the formula, right? So if we said, okay, cool, this hasn't changed, it's 33.5. The radius of the wheel, because its diameter, if I remember right, was 27.5. It's half of 27.5. It must be a quarter short of 14. 13.75. Sorry. $27.5. That's right. So notice that's a pretty big number. 33 times 13. So the linear velocity, like how fast the wheel actually rolls down the road, that's kind of cool, isn't it? So that rotational speed actually turned into linear speed. You see how the radius popped in there? 33.5, I'm just rounding this off. 33.5 times 13.75, 460, roughly 461. Again, that's the velocity of the wheel, or by implication, the bike. Whatever's hooked to that wheel is going to linearly roll down the road 460 inches in 1 second. It's kind of a big number. If I divide by 12, that's actually 38 feet, 39 feet. So it's across this room. This room is probably, that's probably 35 feet. It's roughly across this room in 1 second. That's pretty fast. So again, I didn't ask for that, but that's just kind of cool. That illustrates how you work back and forth and how radius makes a difference. Just to slow down and stare at it a second. Does it make sense? Back here, we used the radius of the cog, but then the fact that those rotational speeds are identical allowed us to go back to the exact same formula. It's just we plugged in a different radius this time. And then we were able to pop out a new velocity. So basically when it all is said and done, we had a linear velocity of the chain of 112, but what did it result in? Like 4 times the amount of speed. I mean, that's what the gear system is doing right there. That's why it's so cool. I only had to move the speed, the chain this fast. If the chain had been hooked to the ground, then that's all the faster I go. But thanks to the mechanism, thanks for this being a small gear, this cog being small and the wheel being large, this moved me way down the road. Now, do you get that for free? The answer is no. You have to work harder. You have to pedal 4 times harder for that to happen. It's not as easy to get that to go up a hill. I'd have a hard time pedaling that up a hill thanks to the big wheel. I'd have to push with 4 times more force on my legs to get that to happen. It's not like you just automatically get 4 times more energy. Well, I asked about angular acceleration. Again, algebraically, when you see something like that, you should think things like this. You should say, well, I don't know. I'm trying to find this thing. So then I just go looking for formulas. Do I have any formulas that have that in it? Yeah, we said the tangential acceleration was equal to alpha times radius. Again, very similar to the equation we just had a second ago. So, do I know any of those things? Well, notice up above, I do know the tangential acceleration is 14. That never changed. That was a constant. Doesn't matter what time it is, that's 14. And if I plug in the radius of the cog, similar to what I just did before, I got more than one radius I could plug in here. But remember, all of that 14 was from the chain, and the chain is hooked to the cog, not the wheel. So I can't plug the wheel's radius in here because the chain is not hooked to the wheel, it's hooked to the cog. So if I put that 3.342 in there, then I get that angular acceleration is 4.189, 14 divided by 3.31342, 4.189. And because this is angular, that would be radians per second per second. So that'd be the angular increase of speed, angular acceleration of the cog. But again, we said that was hooked to the wheel. So that's actually identical to the angular acceleration of the wheel as well. The cog spins faster, the wheel is going to spin faster too. So looking up above, check, found the angular velocity, check, found the angular acceleration of the rear wheel. Those are the two boxed answers. Lastly, theta. I sort of saved the worst for last. Like, what's theta? How do I find theta? Again, you should think, well, what equations do I have that have theta in them? Looking back at your note sheet. The only equation that has theta in it was this one right here, was it not? So it's saying, do you want to know what theta is? Well, you're going to have to know the time. Do we know the time? Oh yeah, we decided 8 seconds. I'm going to need to know something about angular acceleration, alpha. Oh, I know that. So that formula is kind of the ticket here. So let's use it. Let's go new school and take a picture of this thing just to see if I can still do this. Stick it in the notes. Oh yeah, I still got it. Let's go back to black. What about theta? Snap that picture in there. Crop that thing down so we're only looking at what we need. So what do I know about that? Well, assuming that your initial position was 0. In other words, you just said, okay, well, the top of the tire used to be, where did we start? We could have already started with it rotated, but great. And we said it started from rest. So that means its initial angular speed was also 0. You agree with that? So the only thing I have left then is just to plug in the time, which I know. 8 seconds. And we just got finished figuring out the angular acceleration, which for the wheel and the cog was 4.189. So 8 squared times 4.189, you get theta as approximately 134 radians. I won't write this down, but if you take 134 and divide by 2 pi, that's 21.3 laps. So that means the wheel, again, this is important because it's not just like where is it, it's how many times did it rotate to get there, because that rotation is you moving down the road. Isn't that kind of cool to think that you could know exactly where it was, the position that wheel was in? And maybe it's more interesting to think of this as like the Earth flying around the sun, because like who cares what position your wheel's in, but it's like, where's the Earth now? You know, if the Earth was rotating around the sun, where's the Earth right now? To be able to say, oh, it's right here. Can you see how this kind of logic is why people can predict lunar eclipses and solar eclipses, those kinds of things? Like you can know how fast it's going, how fast it's increasing, and where it's going to be anytime in the future you want based on these. So that's kind of cool, I think. Oh, hey, I did want to know about that other question. Then find the linear velocity. I was wondering why I didn't ask that. Seems like such a good question. So what we did up here, I'm just going to move down here. That's kind of rad. Notice I said linear velocity and linear acceleration. Does it make sense in the case of a wheel? You don't care about the normal acceleration of the wheel. You probably would care about that if you're a planet flying around the sun or something like that, because that sense of centripetal acceleration, like all the astronauts get jammed to one side of the rocket, if you will, as a result. You probably would care about that normal acceleration in terms of the people inside it. But in this case, it's linear velocity and linear acceleration. Again, I find myself thinking, okay, linear acceleration, that's a of t. And so I'm just thinking, do I have any formulas that had a of t in them? And frankly, I don't remember. But then I look back and go, oh yeah, I did. We said that the conversion between acceleration linear and acceleration angular was, oh, all you got to do is multiply by r. That's it. Sweet. Do I know r? Yeah, that was the 13.75 because we're talking about the wheel now. And we know the angular acceleration. We said a minute ago that was 4.189. And you might notice the units. That's 4.189 radians per second times inches. So that becomes inches per second. Oh yeah, that is a linear speed, isn't it? So you get like 57.6. So wow, at that time, your bike is increasing by, well, 60 inches is 5 feet. So it's going like 5 feet per second faster. It's not speed, it's going 461, but 1 second later, it's going to be going 60 faster than that. That's kind of cool to know, isn't it? Not only do I know how fast I'm going, but I know how fast I'm accelerating. So it's just going to keep going faster and faster and faster. That's kind of awesome, isn't it?
Tour de France status.
Mm-hmm. Tour de France status indeed. So in my mind, really those last two questions are the interesting ones. We learned about what's happening angularly, and we were able to convert it to what happens linearly. So as I said, ultimately machines of this nature are kind of the backbone of our culture. So being able to convert one to the other, pretty powerful. Now notice in this case though, we actually converted the angular speed. Let's see, that's not true. We converted the linear speed of the chain to angular speed and then back to linear speed of the wheel. So it's kind of linear to angular to linear. So in my mind, this is virtually impossible if you think of this like a physics student that has to think, which formulas do I use? But if I just say, what am I being asked for? And then I look at the fairly minimal number of formulas I have to choose from. I mean, that represents the recipe or the algebraic ingredients to find what I need. And so I can let that do my thinking for me. Well, let's take a look at one more just to make this go in a little bit deeper. And I want you to notice that I increase the realism of this. What's an RPM? Revolution per minute. So the biker is cranking with 40 revolutions in 1 minute. Now, does that seem fast to you or not? Notice it's not revolutions a second. So this is like if it had been 60 RPMs, that'd be 1 revolution a second. Does that make sense? 1,000, 2. That's actually, I don't think that's that fast. So at 40, it's even slower. So this person's cranking at 40 revolutions per minute, but notice they're also accelerating 2. So 40 revolutions a minute, and then 1 minute later, notice it's a minute later, not a second. No, it is a second because I said RPMs per second. So 1 second later, it's 42. 1 more second later, it's 44. 1 more second later, it's 46. So it is slow, and they decided it's too slow. So they're increasing their speed. And would you agree that's what you have control over on a bike? Now you're stuck with whatever leg muscles you have, but you can switch gears to make that happen. But you can pedal as fast or slow as you want. So that's the only thing I have control over is how fast do I spin these pedals? And then, of course, I'm going to go down the road, and that's the question here. So I said at the instant in time, because you're stuck with time, that he finally gets up to 70 RPMs, then find all that cool stuff, omega, alpha, velocity, and acceleration for the wheel itself. And I said for the wheel because that's what I'm doing this for, right? Is for the wheel. Like I want the wheels what's going to send me down the road. Does it matter that this was on the high gear, the 10-tooth cog? It's the smallest cog on there, and I had to pick the 10 because I didn't know what the other ones were, right? I only had 2 that I knew. But this is the gear you're in if you're going downhill or on a flat road, because it's very hard to pedal like this. Because the size of the cog is so tiny relative to the wheel. It's very hard on your legs, if you will. You got to be strong. So your first thought should be, wow, I don't really know what to do with this. I see crank speed there and so forth, but it's like, how do I get in? How do I even, kind of penetrate this world? Well, this goes back to what we just talked about a little bit the other day. Like, for instance, if I say you have 40 revolutions per minute, would you agree that's a rotational speed? Because you're rotating something. But notice the units are not radians per minute or radians per second. So it's not really omega. Omega is radians per second. So how do I get revolutions, a complete revolution out of it? 1 revolution in circumference is 2 pi radians, is it not? So does it make sense my units just went from revolutions per minute to nothings per minute? And isn't that kind of what omega is radians per minute? Now, I could say I'd like the speed to be in seconds, like speed per second, or maybe leave it minutes. I don't know. Since everything else was seconds, I'm going to turn it into seconds. The only way I'm going to get that done is if I have minutes on the top, so those will cancel, and seconds on the bottom. And then I think, oh yeah, 60 seconds, there's 1 minute. So that means if I take my 40 times 2 pi and divide by 60, then my units will be radians per second. Hey, I just found omega. Isn't that kind of cool? So I get 4.19 radians per second, which actually is my rotational speed. So that's kind of cool. Now, what is that the rotational speed of? That's the rotational speed of the crank that you're working on. Do you agree with that? Does it make sense I could do the same thing with 2 RPMs? Since that was my, I won't write the rest of it out, but if I multiply by 2 pi and divide by 60 in that case, I get 0.21 radians. What would the unit of that be? be radians per second. Radians per second, because remember there was an extra per second on the bottom of that last statement. That wasn't just 2 RPMs, it was 2 RPMs per second. So there's a kind of like a per second that comes along for the ride there. And isn't that what we've been calling alpha? Because it's a rotational change of speed, not a linear change of speed. Let's take a look at a kind of a picture of this. I'll just redraw my own picture. If I have this front crank up here, we said this thing was called chain ring. And we said that that was 32 teeth, if I remember right. That was 32 teeth, but the back one was only 10. So it's quite a bit smaller. And the chain is basically wrapped around that. So this was the cog and it was 10 tooth. That's what's going on there. And of course, that's what you have control over. You have control over the chain ring, but the chain is going to take that back to the back cog. So what difference does it make that the front cog is roughly 3 times as big as the back cog? Like, does that matter? What effect does that have? Let's think about that a little bit. First of all, would you agree that what we just calculated here, because the person was cranking at this, that both of these pertain to the chain ring? You agree with that? That's the person cranking. So maybe I call this CR for chain ring. So could we convert that omega to the velocity? Could we convert that rotational speed to a velocity of the chain? Well, didn't we say velocity of the chain was equal to omega just multiplied by r? And since that front was 32 teeth at half an inch, that'd be a 16-inch circumference, and 16 divided by 2 pi then would be the radius of that chain ring, which when I divide 16 by 2 pi, I get 2.546. And that's inches, of course. So if I go over here and I say, hey, I know how fast this thing is rotating. It's rotating at 4.19 radians per second. And I know what the radius of it is. It's 2.546. Again, I'm going to write this in radians. Just look at the units. It's radians per second times inches. So that'd be inch radians per second. But remember, radians really aren't a unit. So you have inches per second. So I actually get the velocity then of the chain as roughly 14 inches a second. But does it make sense now? I can kind of hop back to the back and see what that's doing in the back. Or I don't know, maybe I'll need this later. Let's just calculate it while we're here, because we can. That'd be the linear velocity of the chain. What would be the angular, or the acceleration of the chain? We said that was the angular speed times the radius. So didn't we figure out a second ago the angular speed of that crank was 0.21? And we said its radius was 2.546. If I multiply those out, I get acceleration as 0.7. Or maybe I'll write out front. That all of that pertains to the chain. So I know how fast the chain is moving now. I turn the rotational speed of my crank into linear speed of the chain. So stop and think what that means. Remember, that means he cranked at 40 revolutions per minute, which gave him a speed of 14 inches per second. But then he was increasing his speed by 2 revolutions a minute, which means he's increasing the chain speed by 0.7 inches per second. So, you know, what's the speed of the chain? Well, like, again, we got to have a snapshot in time. And it said the snapshot in time was when he reaches 70 RPMs. So if I crank at 40 revolutions a minute, how many 2s does it take to get me up to 70? That'd be 40 plus 30 is 70, so N would have to be 15. Or perhaps I should say, since that was per second, I should really call that time, shouldn't I? Two RPMs per second. So in 15 seconds, that'd be 30 more added to the 40, it'd be 70. So does it make sense? I could have just said time is 15 seconds as the snapshot, but maybe the biker doesn't know that. He just knows he's moving from one crank speed to another. Well, take a look at the formulas we have to work with. One of them I'm looking at these two formulas now. This says if you have an initial angular speed and you have an acceleration in a time, then you can find out your angular speed later. Does it make sense? At 40, we had our initial angular speed, but now time goes by and it's actually going to be going faster. So I think that's the equation I need. All that dude over there. That's so cool. We can make it bigger. I have to work at it. So let's see, I knew my initial angular, and this is hard, I find this hard. This initial angular speed, because he was going 40, that's his initial angular speed was 4.19. Do you agree with that? Hurt your brain. This was his initial angular speed. We just figured out that 15 seconds went by, and his angular acceleration, we said, was 0.21. So we have 15.21s to add to 4.19. So that means omega at the end of all of this is 7.434. Don't we have the analogous velocity equation, the linear velocity equation that says if you take acceleration times time plus the initial velocity, then you'll know your final velocity? Didn't we just figure out the velocity of the chain was starting out 14 inches per second? Actually, I suppose there's an easier way to do this. Actually, let's just see if it works. I actually don't know. We said the time was 15 seconds and the acceleration tangential was 0.7. 0.7 times 15 plus 14. As a side note, that was the first equation that occurred to me, but didn't we have an equation that converted this? A minute ago, we said, didn't we say if you take R and multiply it by, do I have this right, omega, that will give you the velocity? What's that?
Omega squared.
I think that was the acceleration one that was squared.
Oh, just kidding.
So I could have said, okay, omega, we just calculated as 7.34, and the radius of that cog in the front was 2.546. No. Why do I have two different numbers written down? That front cog was 32 teeth. Radius was 2.546. Getting a different answer for this. Why am I getting a different answer?
Well, so shouldn't it be the 7.34 times the 2.546?
Mm-hmm. But I'm getting a different answer. I thought I was going to get 21.3 again, just out of curiosity. That's the answer.
The tangential acceleration. When I plugged in my calculator, I got like 0.5. 0.7.
Got it. So you're saying there's actually a mistake back here. Like if I take this acceleration right here, I crossed something out on my notes and I'm looking at it and I'm kind of trying to figure out where I screwed it up now. So I think you're right. 0.21 times. .53. That's exactly right. So this one isn't right. It's 0.53. So I'm hoping these two agree. So fixing that, if I take 14 plus 0.53 times 15, I get 21.95. I'm hoping I get the same answer over there on the right, 7.34 times 2.546. Nope. This is good for us. We don't have a lot of time here, but this is good for us. Let's just think about this for a second. What's wrong here? Kind of rechecking because now I'm thinking about stuff that I calculate, punch numbers in, and maybe I'm rechecking. I'm checking this 14 right here, 4.19. Yeah, that 14 isn't right either. 4.19 times 2.546 is 10.67. So if I change this 14 down here to 10.67, there we go. Now they agree. Better throw that note sheet away. So these agree. Well, they would if I had carried the decimal places out a little more carefully. So it's just kind of interesting. Again, I only say that just so that you have a sense of, like, I got more than one formula that's got velocity in it. So that's kind of cool that I could have used either one of those and got the same answer. Okay, so quickly then let's work our way back to the wheel. So the main thing is that the main thing is now that we just got finished with kind of what's happening on the front cog and what's happening to the chain.
Radius of the back cog.
That's exactly right. So now we can take the back cog, which has a 10 tooth. So let's move to the back. Cog.
So the first velocity of the chain is 10.67. But what was the velocity of this round?
This was the 10.67 was the velocity of the chain when he was cranking at 40.
Okay.
And then after he got to 70, then everything was increased. And so good question. So he was going 10.67 when he was at 40, but then by the time he got up to 70, then it went up to 18.6. Got it? That's a good question. So maybe I'll go back and say this is the velocity initial. this is the velocity final. That'd be good. So if that back is 10 tooth cog, that means it's a 5-inch circumference. And since that's equal to the 2 pi times radius, if I take 5 and divide by 2 and divide by pi, I only get a radius of 0.796. So the radius of the cog in the back, 0.796 inches, way smaller. So let's convert now these velocities up there to rotational velocities. And again, I'm interested that you see why we're doing this. Because I started with the rotational speed of the front cog, turned it into a linear speed so that it got on the chain. And now the chain is hooked to the back cog. And so I want to turn it back to a rotational speed, because whatever the rotational speed of the back cog is, that's the rotational speed of the tire. So now we're going to be able to move down the road. So what's our conversion? Thanks to that radius, since I know the velocity is equal to angular velocity times radius, if I say, okay, that's cool. I know the radius of that rear cog is 0.796. So this would be the angular velocity of the cog. I know the velocity of the chain. I know the linear velocity of the chain was, now I kind of don't know which one to use. I guess I'll use 18.7. Then I know the angular velocity of the rear cog, which means I also know the angular velocity of the wheel, what is 18.7 divided by 0.796. That bumps up to 23.5. So I now know how fast the rear wheel is spinning. Well, what if I want to know how fast now the rear wheel is going down the road? Well, let's go back to the same exact calculation. I have V equals omega times R, except for now I'm talking about the radius of the rear wheel and the angular velocity of the rear wheel, and the linear velocity of the rear wheel. Well, again, this is why the conversion is so cool. The angular velocity does not change moving from cog to wheel, but the radius of the wheel changes because it's 13.75 inches. So if I multiply that, 23.5 times 13.75, I get 323 approximately. So the velocity of the rear wheel is roughly 323. Again, I don't remember which question I asked now. We'll go back and look at it in just a second. But remember, this is like we just reached, I don't know, a finish line of sorts, in the sense that we were cranking in the front with a certain speed and a certain acceleration. And we basically said, how fast am I going down the road as a result of it? This is no different than the previous problem that we did. That's kind of the idea here. Maybe in the interest of time, we should just stop with that velocity. We could go on and find the angular acceleration and the acceleration tangent here. In other words, yeah, he's going 323 inches per second, but remember that was at a snapshot in time, and we actually figured out that was 15 seconds later. So could we also find acceleration of t at 15 seconds? Because you're not going to stay at 323. We could, but I don't want to make you stay longer. So this is kind of hard in the sense that there's a lot of things to think about, but it's also kind of easy as long as you just use your algebra formulas to work from thing to thing to thing. But I think it's just really important that you see the transition between the chain how it causes the linear speed of the chain causes the linear speed of the front cog and the back cog to be identical. But the angular speed of those is not going to be identical. The front one, if it's small, is going to have to spin much faster in order for the back one to keep up with the back one, so to speak. If I have a kid's bike with tiny little wheels and it's going down the road, it's going to have to spin way faster to keep up with the dad bike that has kind of big wheels. So rotational speeds are not going to be the same. So the fact that the chain connects one to the other and how that all works is really kind of cool. All right, let's leave it at that. I would